So for this physics of sound lecture, this is meant to supplement the notes that you already took when you did your research. However, let me clarify, there are topics, ideas, concepts that are presented in this lecture that were not asked of you on that research assignment because I didn't feel the topics were able to be researched by you, that they would be too complex, and so I just left them out. They will be added in here, and subsequently you need to understand these ideas and topics, and if you care to, add them to your notes. First of all, here's our list of definitions. I'm going to go through each one of these. First of all, audible sound is merely sounds that humans can hear. Sounds that humans can hear typically fall between 20 hertz and 20,000 hertz. That's what it means to be audible sound. It means it can be perceived by the human ear. There are sounds below 20 hertz and sounds above 20,000 hertz. Those are called infrasonic and ultrasonic. The ultrasonic are on the high end, the infrasonic are on the low end. They are sounds being generated that our ears just cannot perceive, but they are still sounds being generated. There is wave energy being transmitted through the air. Our brains and our ears are just not set up to register those sounds. Elephants can hear very low frequency sounds, and bats and dolphins can hear ultra high frequency sounds. If you're familiar with the concept of a dog whistle, you blow on a dog whistle, you and I can't hear it because it's in a frequency range that's over 20,000 hertz. So our ears do not detect it, but dogs hear at a much higher frequency than we do. Now, pitch. Pitch is described as the highness or lowness of a sound. And you understand something like a flute, you can visualize or you can hear in your mind the sound that a flute makes. We say it has a high pitch, it's a high sound, but a tuba, on the other hand, makes a very low sound. What you're describing there is the pitch. And I can give you some examples of this with an online tone generator. That right there is a fairly low pitch of a sound. That is a much higher pitch sound. Now, an echo. An echo is when we get sound waves that hit a new medium. The place where two sound waves meet, or two mediums meet, is called a boundary. And when sound waves come out from a sound source and they hit a boundary, some of the energy is always reflected back. And we saw this in our wave lab. When we made waves in our spring, the energy went down to the end and it bounced back. Now, some energy is transmitted into the new medium. And you felt this when you were holding the end of the spring. You felt some of the energy coming to you, but energy is reflected. Now, what an echo is, remember, this is a sound wave that we're talking about. So if the sound energy comes back to your ear, you hear the sound. That's what an echo is. But an echo is a sound wave that comes back to you clearly, and you can hear the original sound exactly as it was when it emanated from the source. It doesn't sound distorted. It doesn't sound warbled. You call out your name and you hear your name come back to you. Now, echolocation. Echolocation is when certain animals, like bats and dolphins especially, send out sound waves and they bounce off an object and it comes back to them clearly. That's what an echo is. They hear these ultra high frequency sounds that you and I can't hear, and then they can perceive where things are. They can perceive a distance. Hey, I sent out a sound wave and it echoed back to me. And depending upon how long it takes the echo to come back, a bat or a dolphin can determine the distance between itself and the object that its sound waves bounced off. So echolocation, in a nutshell, is using sound waves that bounce off an object to determine the distance between two objects. Now, sonar is what we do in submarines. It's our version of a mechanical echolocation. It stands for sound and navigation and ranging. So submarines underwater, they can't see because light doesn't travel very far through water, but sound waves travel very well through liquids. And so if you send out a sound wave, and it hits something else that is not water. It is a new medium. It is therefore going to be reflected back. And you can time how long it takes the sound waves to go out and come back, and that'll tell you how far away an object is, how big the object is based on how big an area of sound waves come back to you. Now, a reverberation is different than an echo. A reverberation is still a bouncing off of sound waves, but the difference is that a reverberation is a mix of sound waves coming to you at different times. An echo, the sound goes out and comes back to you all together, and you hear the original sound. But think about something here like a concert. You hear the sound, especially if this is, say, a non-amplified, there's no speakers. Somebody's on the stage playing, and the sound comes to you straight like that. And it takes a certain amount of time for the sound to travel to your ear, and you hear it. But the sound waves go out in all directions. And the sound wave that bounces off the ceiling and then bounces to your head gets there a little bit later than the one that was coming in a straight line. This sound wave that bounces off the ceiling, bounces off the back wall and comes to you is a little bit more delayed than the one that bounced just off the ceiling. So what you perceive, what you hear, is many different versions of the same sound, but they're coming to your ear at different times. And hence, you don't hear a crisp, clear sound. That's what we call a reverberation. It's sound waves coming to your ear from a sound source at different times. This is especially bad if you have a microphone that is sending sound out, say, through a speaker. So if you're sitting right here, you would hear the sound first. You also hear it come through the speaker. If it bounces off the wall and back into the microphone, it gets transmitted twice. And so you hear a jumbled or a warbly or a not clear sound. That's what a reverberation is. Now, sound intensity refers to the loudness or the energy of the sound. The relationship I want you to understand here is that as you go away from a sound source, the energy or the intensity of a sound wave decreases. And this is common sense. You know that the further away you get from a sound source, the softer the sound is. And here's why. Because sound goes out in all three dimensions, if you're standing right here, the energy, we'll say the energy from this speaker is in an area of this size. Well, you get a little bit further away from the speaker, and that energy is a lot more spread out. So the energy from the sound is going to be weaker because it's spread out over a bigger area, which means a lower or not as loud sound. Out here, the energy is going to be spread over a bigger area. And eventually, the energy gets so spread out that you can't hear the sound. That's what intensity is. And it depends upon the distance from the source and the original energy of the sound. Now, the decibel. The decibel is abbreviated dB, and it is the unit to measure sound intensity. It's the one that's most commonly used. Decibel was for Alexander Graham Bell, the inventor of the telephone. So you get the connection there. And there are some charts that kind of give you a relationship between how loud a certain sound is and what would it be in decibels. So you see something like this, 20 decibels, leaves rustling. 60 decibels, two people talking back and forth. A hairdryer, 90. A police siren, 120. Fireworks, 140. So the decibel is just a unit of measure for how strong or how intense a sound is. Now, the threshold of hearing and threshold of pain. Threshold of hearing refers to the point at which humans can hear sound. There is a certain threshold, and we've already seen that the frequency helps to determine that because we can't hear all frequencies. So there is a certain threshold at which we can hear sound, but it's not just frequency, it is also intensity or energy, because a sound can be in the audible range, but if it doesn't have enough energy, we won't hear it. The threshold of pain is the point at which a sound becomes painful or uncomfortable to the ear. And that can also be a function of frequency, because high-pitched sounds we know bother our ear. And it can also be determined by the amount of energy, because we know louder sounds can hurt our ears. Now, the natural frequency, things vibrate back and forth. And I want you to think about a child swinging on a swing. It has a certain rate at which it will move back and forth. And when we push a child on a swing, we always try to push with that natural frequency. We push it at the right time in the right way, and it keeps the swing going back and forth at the frequency at which it wants to move. You would not push a child on a swing like this, because you are not matching the frequency at which the swing wants to move. All things, when they vibrate, they have a frequency at which they want to vibrate, and it's said to be their natural frequencies. And just like a pendulum, a longer pendulum and a shorter pendulum don't swing at the same rate. All different materials out there in the world will vibrate with different frequencies because they're different stuff. This leads to what we call a forced vibration. This is a tuning fork. It's a metal Y-shaped object, and when you hit it, it will vibrate back and forth. Metals are very malleable. They bend and they shake kind of easily. So when the top ends of the tuning fork move back and forth, it causes the air to move back and forth because the tuning fork is vibrating back and forth. Well, we are forcing the air to vibrate at the same rate that that tuning fork wants to vibrate at. So that's what a forced vibration is when one thing forces something else to vibrate. Now, resonance, on the other hand, is a little different. Resonance is when you have one thing that makes another thing vibrate at the same natural frequency. So we get this tuning fork moving back and forth, and then those vibrations come over here and they vibrate this tuning fork back and forth at the same rate. Well, what we end up hearing is a deeper, more resonant sound, a louder sound, because now I've got two things vibrating back and forth the same way. I'm going to hear a deeper, more powerful sound. Now, sound damping, we get energy coming out, say in a movie theater speaker, and I'm sitting right here in the movie theater. I only want to hear that sound come to me once. I want to eliminate reverberation because I want to hear the sound clearly. When sound hits the side of the theater, it has a tendency to want to bounce off and come to my ear. So the sides of theaters are covered in soft materials, either a carpet or foam, or in the old days, drapes. And the energy would hit these soft drapes and kind of wiggle the drapes a little bit, and then it would not have the energy to bounce off loud enough to hit my ear. Recording studios use things like this. They use foam so that when any extra sound hits the wall, it doesn't bounce off. It just squeezes the foam and gets caught up in there. Our classrooms have these ceiling tiles, which are primarily there for sound damping, because our roof here is metal. And if we didn't have those ceiling tiles up there, we would get a lot of reverberation back and forth, and we wouldn't be able to hear very clearly. So this is one of those first concept questions about what kind of materials are best for sound damping. Things that are soft or things that are squishy, because when sound energy comes in, the energy is used to squish together the soft material, and that means there's less energy to bounce off. If you have a metal roof or a tile floor, anything that is really, really hard, well, they don't squish. So that means the sound energy that comes in, almost all of it will bounce right back off, and I get that reverberation effect. Here in IA, we live in a big fishbowl with lots of hard windows, lots of metal surfaces, tile floors. If you look at the hangar, it has primarily a bunch of hard surfaces that will bounce sound off very easily, which means you get a lot of reverberation. The other day, we had some students playing up here on the stage, and the sound quality wasn't great. And it wasn't any fault because of their instruments, but what was happening as they were sending out sound through this speaker, it would hit the windows and come right back to them and then get sent out again through the microphone. And if you're standing right here, Well, you would hear the sound the first time, and then you would maybe hear the sound bounced off the window, and then you would hear the second sound that had reverb through the mic, so you don't get a good, crisp, clear sound. In our hangar, though, there are some things that we do to try to help dissipate some sound energy. This shape of the wall is that way so that sound energy kind of goes in these little openings in here and it kind of bounces around inside of there, and you get less energy bouncing back than if the wall was flat. Because the metal roof up here would reflect so much sound energy and cause a lot of reverberation, these softer panels are put up there so that when the sound energy kind of goes up, it kind of bounces around in there and doesn't come back out. A wave front is exactly what it says it is. It's the front end of the wave. It is the front of the compression from a sound wave. So there's a wave front, there's a wave front, there's a wave front. That's the leading edge of the compression of a sound wave. Now, how is sound created and transmitted? Sound is created when some energy is used to push air or compress air. Well, nature doesn't like things to be squeezed together unnaturally, so it's going to unsqueeze itself. So a tuning fork, as it pushes this way and it grabs a little chunk of air here and it squeezes it together, then the air will unsqueeze. But as that air unsqueezes, it squeezes together the next set of air, and over again. Speakers, if you've ever seen a speaker, you can actually see speakers push forward and then go back, and push forward and go back. What they're doing is they're creating those compressions. They're squeezing together air that then unsqueezes in a compressional wave, and that's how sound is transmitted. So how do we hear sound? Well, our inner ear basically has a little drum in it. It has a little membrane that when air is being pushed and these little compressions come in, and it pushes against this flap, this eardrum. And our eardrums vibrate, and they'll vibrate at anything between 20 and 20,000 hertz. And our brain is hardwired to read those vibrations. And this is why we can detect a wide range of sounds, because the rate at which the compressions come in changes what I perceive, the pitch or the highness or the lowness of the sound. Now, why do you hear yourself differently than how other people hear your voice? Remember, if you've ever heard yourself on a tape and you say, I don't sound like that. Well, yeah, you do to everybody else. When you talk to somebody else, you are making compressions and rarefactions through the air, and somebody else hears your energy transmitted through the air. However, for us, here's our ear. We not only hear the compressions and rarefactions come in through the air because our ears are out there in that air, we vibrate our vocal cords to push the air out of our mouth. Well, our vocal cords are in our body, so when we vibrate our vocal cords, we vibrate all the other stuff in our body. And my ear is connected to the rest of my body. So when the rest of my body vibrates, I perceive some vibrations through my body as well as through the air. Well, somebody else is only getting half those vibrations. They're only getting the vibrations through the air. They don't get the vibrations through their body because they're not the ones making the sound. So this is why you sound differently to other people than you do to yourself. Now, what type of waves transfer the energy in sound? These are always compressional waves. You can see there's a compression, there's a rarefaction. Compression, rarefaction. It's about squeezing together air and then having it unsqueeze. The relationship between frequency and pitch. Think of these two bells. If you were to hit that bell and hit that bell, even if you hit them exactly the same way, the same sledgehammer, same energy, you know you would get a different sound. This one is going to be a higher tinkly kind of sound, and this one's going to be a very deep or low pitch sound. The difference is, how does the metal vibrate? Think about which one is going to shake or wiggle or vibrate back and forth more. That's going to be this one. it's going to have a higher frequency of vibrations. This thing's not going to shake back and forth very frequently because it's a big heavy bell. So the relationship between pitch and frequency is the higher the frequency, the more it's wiggling back and forth, the higher the pitch of sound you hear. The lower the frequency, the lower the pitch you hear. Now the Doppler effect. The Doppler effect refers to the sound emitted by a source when it is moving. So most sound sources, we think, oh, there's a speaker right there and it's in one spot and the energy comes to us at a certain rate, a certain frequency. So I hear a certain pitch. But if a sound source is moving, if it's doing something like this, if I'm standing right here, the car, imagine like it's a siren from a police car, it makes a sound, but then it's moving towards me, so now the next sound is closer to the first sound, and the next sound is closer to the sound ahead of it. So what you end up having is you have sound waves tighter together on the front end, the direction that the sound source is moving. And the opposite is true on the back end. As the sound source moves away from you, it made a sound here, and then it made another sound, but it was further away when it made that same sound. So it takes a little bit longer to get to you, so the waves aren't as frequent. So the Doppler effect changes the frequency of the sound that you hear. If the sound source is moving towards you, you can see the frequency ends up being higher. If the sound source is moving away from you, the frequency ends up being lower. Well, remember, the frequency determines the pitch. So if I'm hearing a siren come down the street, as it's coming towards me, I hear a much higher pitch sound. And after it goes past me, I hear the pitch actually change, even though it's the same siren. That's what we call the Doppler effect. It's the changing of the frequency of sounds due to the movement of the sound source. Now, the characteristic of an elephant ear. This is one thing I didn't put on the quiz because this is a tough understanding. But elephants have really, really big ears, and they can hear very low frequency sounds. And I'm going to draw a low frequency, long wavelength sound, something like this. There's my human ear. The wavelength is so long that it basically missed my ear. Well, if it missed my ear, that means I can't perceive the sound. I can't hear it. But due to the size of an elephant's ear, a very long wavelength can't miss an elephant's ear. It's going to greatly increase the chances that it gets hit by those long wavelengths or low frequency sounds because the ear is so big. For us, think about a higher frequency wave. No matter how you draw that, it's going to hit the human ear and we are going to be able to perceive it. Now, how are ultrasonic sound waves able to produce images, but infrasonic sounds cannot? Remember, ultrasound are sound waves, and sound waves, when they hit something, they bounce back. So a baby in utero, we send sound waves in there, and then when the sound waves hit a different medium, it bounces back. Well, a baby especially is inside of an amniotic sac filled with fluid, which is one way in which one medium for energy, sound energy to go through, but then it hits the baby. And so, oh, this is a different medium, and it bounces back. And we can take a picture based on the pattern that the sound waves come back to me. But infrasonic waves, ones with big wavelengths, don't work very well. Especially with something small like a human fetus in utero, the wavelengths would probably just wrap around the fetus, and I wouldn't be able to get a good, clear picture. Now, is there a chance that some of the waves would hit? Sure. But I don't get a lot of them bouncing back, so I don't get a clear picture. If I had a really, 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 really high frequency wave, they are going to bounce back from the fetus more often, and I'm going to get a more clear picture because I'm getting more waves bounce back to me. Now, some advantages and disadvantages of ultrasound. Once again, another concept question. We use ultrasounds a lot, primarily for taking sonograms, sono sound, sonograms of developing fetuses because sound waves are relatively harmless. They don't harm tissue in the body. So it's just sound. It'd be no different than yelling at somebody. Your sound waves really can't cause any physical damage, even to the developing cells, say, in a fetus. Whereas something like X-rays, you wouldn't want to bombard a fetus with X-rays. They are damaging to cells, especially developing cells. So sonograms are very low risk propositions. They're not going to cause any damage. So that's why we use them. But the disadvantages of ultrasounds. Well, these sound waves, they don't give us the clearest picture. They can't give us a lot of detail. They also can't go inside of bones. So we can't take a picture, say, of a broken bone because the sound waves don't bounce well off of bones. Now, what determines the speed of sound in a particular medium? This is one thing a lot of you missed on the quiz. This is what most of you found, the density and elasticity. All right, now density, I'm going to pair that up with temperature. If you've done a little bit deeper dive, you would have seen that the temperature is the primary thing that changes the speed of sound in a particular medium. The elasticity also goes back to temperatures. Elasticity is how are the particles bouncing off each other? Well, the temperature. The temperature refers to how fast the particles are moving. And that's going to change the elasticity, or how they bounce off of one another. It also changes the density, because we know that hot things like to expand and cold things like to shrink. So the temperature definitely affects the speed of sound in a medium. Now, why does sound travel faster in solids than in liquids? Remember that sound is transferring energy. It's squeezing something together and then unsqueezing. If you think about a solid, all the particles in a solid are really close together. So if I jam some energy into this guy right here, he immediately transfers it to this guy, immediately transfers that guy, immediately transfers, and the energy gets passed along really quickly from particle to particle because they're touching. They don't have to go anywhere to transfer the energy. Now, if you think about a gas, if I give this guy some energy, he has to move over here and then give this guy the energy. And he says, okay, I'm squeezed together. Now I've got to go over here and I got to squeeze together with this guy. And then squeeze together. Well, there's a gap in between particles of a gas. So it takes a little bit of time for that squeezing and unsqueezing to happen. And this is why sound travels slower in gases and much faster in solids. And liquids, of course, are somewhere in between. Now, why does sound travel faster in wet air versus dry air? Think about dry air. We'll say we have 6 air molecules here. Wait, I need to erase. Air molecule, air molecule, air molecule. Let's do 5. Well, and I give some energy to this air molecule, and it's got to go over here and squeeze together with this guy to then transfer the energy. It takes a certain amount of time. If I have wet air, here's my air, and I'll draw my H2O as blue. You can already see that the energy transfer is going to happen quicker because this guy's going to get the energy. Oh, there's some water in the way. That water is going to take the energy. He transfers it to the next guy. So because water, humid air, is more dense than dry air, sound travels faster in wet air than it does in dry air. That's because there's more stuff in the air and it has a greater density. There's more stuff closer together. Now, why are sound waves usually drawn in circles? And this is how we're going to represent them, because sound goes out in 3 dimensions. Sound just doesn't go forward from your mouth. Somebody behind you can hear you. And this is typically how we are going to represent sound being drawn. As waves, you want to think about it as a compression, a rarefaction. That's the compression, rarefaction. That's the compression. So the lines we generally refer to as that squeezed together part. And the open space between the lines, well, that's the stretched out part. The only exception to this would be if we had a sound source that was up against a boundary. We might draw half circles. But we generally describe sound waves and waves in general as circles coming out from a source because they go in all three dimensions. Now, how can sound waves be used to determine distances? Well, if we know how fast sound travels in a particular medium, we know what the temperature is, and we listen for the sound and we time how long it takes, it's a simple V equals D over T proposition. We know the velocity in a given medium, and if we time how long it takes the sound to get there, we can calculate the distance. And this is how sonar works. Underwater, a submarine knows how fast the sound is traveling through the water. They know the temperature of the water, they know the density of the water. They send a sonar wave out and they time how long it takes to come back, and that will tell them the distance something is from the submarine. Now, how does the movement of a sound source affect the pitch? Well, we did this with the Doppler effect, but we just didn't say pitch, but we did describe the frequency. So in front of the moving sound source, we know the waves are going to come to you more frequently, which means you're going to hear a higher pitch. If you're behind the moving sound source and it's moving away from you, the waves are going to come to you at a lower frequency, which corresponds to a lower pitch. The formula for sound intensity is this right here. I did put this on the quiz because I know there were some other variations that were given to you. This is power, or how powerful is the speaker or the sound emitter. And think about power. Power is work divided by time. Think about the work of moving air. A more powerful speaker can move more air more quickly. So we get the power side. This right here stands for, or is the formula for, the surface area of a sphere. And because sound goes out in all three dimensions at once, the intensity or the loudness of the sound is, okay, how much power do you originally have? And then how far spread out is it? How big is the sphere? So a certain sound source, like a speaker, is going to have an intensity here, a different intensity here, a different intensity here. Because as you get away and the sphere gets bigger, that sound becomes a little bit more spread out. Now, here's a thinking question. Which one of these two would have a greater intensity? And this is a trick question, because if this bee were in your ear and buzzing, it might sound really, really loud. If this cannon, which we know is something like a cannon, would produce a very loud or intense sound, but if it's 5 miles away, it might not be as intense a sound as a bee that is in your ear. And that's because the distance from the sound source directly impacts the intensity or loudness of the sound. So why do we sing in the shower? If you do sing in the shower, well, think about a shower, a lot of hard surfaces, and has a set distance. We stand in the middle of the shower and we make a sound, and it goes out and it hits the hard surface of the shower, and then it bounces back. But it's a pretty small area, so the sound comes back to us pretty close to in sync together from each wall and from when we first made it. So what we hear in the shower is some nice resonance. We get all of that air in the shower kind of resonating at the same frequency at which we emit the sound. And we hear a nice, full, deep, richer sound than we can make on our own. So we like that quality of the sound, so this encourages people to sing in the shower. And typically, men sing in the shower more than women. And this is because of the length of a shower. Men typically produce lower frequency waves, and that works well with the wavelength or the distance of this shower. Not saying that women can't sing in the shower. I'm saying that the frequencies that are formed from the resonance typically works or sounds better with the frequencies that men generate.